The RoboMaster competition, an annual robotics contest held by DJI, gathers teams from universities worldwide to participate in rounds of robot v robot combat, aided by computer vision. The main competition at this event is a 3v3 battle, where teams design and build custom robots to engage in combat by shooting projectiles. To score points in the competition, you must accurately hit the opponent's robot's armor plates with a 17mm or 42mm ball. These armor plates are equipped with lights and numbers and sensors. Damage is only registered when these plates are hit. This unique aspect of competition emphasizes the importance of computer vision and object detection capabilities, as robots must quickly and accurately identify and target the armor plates of their adversaries to score points and ultimately achieve victory. Our goal is to be able to detect RoboMaster armor plates with high accuracy. We will do this using an object detection machine learning model called YOLO V5 that is optimized with TI Deep Learning Products proprietary Onyx build. And then we deploy this model to a BeagleBone microcontroller equipped with an Intel RealSense camera to achieve high frame rates. We collected images collected by Purdue and labeled the armor plates attached to competition robots in these images.
YOLO V5 is a computer vision model commonly used for object detection, and it is known to process images quickly with a high degree of accuracy. The YOLO V5 network is made of three pieces: the backbone, the neck, and the head. The backbone is a convolutional neural network that takes an image input and forms image features by putting it through different layers. The neck merges these images features together to make a prediction. The head forms a class prediction based on the acquired features, which overall creates a sparse prediction of the location of the detected object. The YOLO model takes the RoboMaster images with labeled armor plates and uses training techniques such as data augmentation and loss calculation to learn how to detect the armor plates.
Our dataset was provided by the Purdue and UT RoboMaster teams, which consisted of videos displaying their robots. The robot with blue lights was labeled with a blue label, and the robot with red lights was labeled with a red label. We labeled these images on a publicly available website called cvat.ai. If the image was too blurry or both lights on the robot's plate were not visible, then we would skip that image in an effort to avoid false positives. Each group member was assigned roughly 500 images to be processed. Once our labeling was complete, we exported the data as YOLO 1.1, and we were ready to begin integrating with the BeagleBone board.
There were 4 steps for us to enable deployment of our model to the BeagleBone. The first step is initialization and configuration. Booting of the BeagleBone is done through the latest Debian image flashed onto the eMMC. The second step is to install firmware. We installed BeagleBone device trees package for initialization. Additionally, we installed Python and all required libraries for running YOLO 5 model and the Intel RealSense cameras to enable communication between the camera and the BeagleBone board. The third step is to enable internet access to the BeagleBone. After configuration is completed on the Beagle board, the internet is available using a USB connected to a Windows computer. The Python wrapper is then built from the source. After this initial configuration, we were able to correctly integrate the object detection model with the BeagleBone and the Intel RealSense camera.
We tested our model on the images provided by the UT RoboMaster Stampede team. At first, it had trouble in properly labeling plates with red light, but we were able to reduce this error and improve our accuracy by tuning our parameters. We ended up lowering the learning rate by a factor of 15 times and lowering the resolution because smaller images have faster inference times. These significantly improved our accuracy. In the images, you can see how the metal plates are properly labeled, and the image with a lack of plate has no labeling. There are some false positives when the image is too blurry or there is an overwhelming presence of blue or red lights. Overall, the detection model performs excellently.
In conclusion, we used the YOLO V5 model to successfully detect RoboMaster armor plates on a BeagleBone AI64. Our process consisted of labeling armor plates, using Open Neural Network Exchange to maximize the performance of the model, and training it on the BeagleBone. Our results showed that the model performed well due to lowering the resolutions and learning rate. Given the time constraints, the biggest difficulty we faced during the project was understanding how to use YOLO and programming it onto the BeagleBone. One way we can improve this project is to label more images, but this manual labeling process is very tedious on the computer vision tool.